We have been focusing on making comparisons between two probabilities of success by looking at their difference. In other words, take pi1 minus pi2. And with this difference, it's very important to know, is the difference equal to 0 or not, because that tells us, is pi1 equal to pi2? There are other ways to make this comparison between these two probabilities. In particular, we could take the ratio, pi1 divided by pi2. This ratio has a special name. It's called a relative risk. It will be clear as we go along through some medical applications why it's called relative risk. But the purpose then of this particular section of the notes is to talk about when is this measure better to use or more important to use than looking at the difference. And then also to look at how we can estimate this ratio and how can we make inferences about it. Now, one place where probably all of you have seen the relative risk used in practice, although maybe it probably wasn't referred to as a relative risk, is with respect to in the news media when some kind of scientific study, often some medical study, is stated. So, for example, probably all of you have heard something like this said in the news media by a reporter. The researchers showed that an individual was blank times more likely to get some bad disease if they did a bad behavior than if they did a good behavior. Now, this measure, as long as the reporter knows statistics enough, this measure that they're reporting is this one right here. Unfortunately, though, reporters can actually report some other measure, particular one that we will see in another set of notes called an odds ratio in this particular setting. So anyway, let's talk about how we can look at the relative risk here. Now, when is the relative risk of interest? Well, let's consider these two different scenarios where we have maybe a clinical trial and we're measuring, does some kind of new drug provide some kind of adverse reaction to people after they take it. So in this kind of a setting, they're going to measure adverse reaction, yes or no. That's our binary response. Our two groups are a person's received a drug or they received a placebo. In this particular setting here, suppose that somehow we know what the true probabilities are. The probability of adverse reaction if you receive the drug is 0.51. For placebo, it's 0.501. So the difference is just 0.009. Now consider this other scenario where everything's exactly the same, but now I've changed the probabilities to be pi1's 0.01, pi2 is 0.001. So in both cases we have, let's say, it's a somewhat of a rare event to have an adverse reaction. Notice the difference here, as in previously, is also 0.009. But there's something that's very important here that the difference in the probabilities here does not capture. And this difference is exactly the same no matter what the size of pi1 and pi2 are. So we see this in this particular example. But in this particular example, we also see that people are 10 times as likely, I should say, to have an adverse reaction when they take this drug than when they don't. And in medical settings, that's very, very important. So you've increased your risk of getting an adverse reaction by taking this drug. You're 10 times as likely to have this adverse reaction. And so that's why in situations where the probability of success that we're working with is small, it's better to use a relative risk than to use the difference of those two success probabilities to interpret the results of a particular, in this case, study. So, what the relative risk allows us to do is helps us to understand the relative magnitudes of these changes of these probabilities across the two different groups. The relative risk is formally defined as, let's say, RR, and it's equal to pi 1 divided by pi 2. Now here are some ways to interpret this relative risk. As I was kind of alluding to before, sometimes the relative risk can be misinterpreted. So it's very, very important to get this correct. So we're going to spend some time talking about the interpretation here. Think of these interpretations here as templates for your own interpretations. So in that second scenario, where the relative risk was equal to 10, here's a standard interpretation. An adverse reaction is 10 times as likely for those individuals taking the drug than those individuals taking the placebo. So notice how we have, you could say, group 1, and we have group 2 here. And I'm saying 10 times as likely. Also, I could say the probability of an adverse reaction is 10 times as large for those individuals taking the drug than those individuals taking the placebo. Do note that words like likely, and probability mean the same thing. This is going to be important, especially with the next set of notes coming up. Actually, I'm sorry, next subsection of notes. Now, an alternative way to phrase this particular interpretation is as follows. An adverse reaction is 10 times more likely for individuals taking the drug than for those individuals taking the placebo. Or I could also say the probability of an adverse reaction is 9 times larger for individuals taking the drug than the individuals taking the placebo. So notice I'm using 9 there instead of 10. So why do I use one interpretation that uses a 10 and another that uses 9? Well, it ends up coming about through the reason ends up coming about through these words that I'm using. These they have slightly different meanings, more versus as. So here's some help to understand what's going on here. So here are two equivalent statements: 3 times as likely or 2 times more likely. This would result in a situation where, let's say, pi 1 was 0.75, pi 2 was 0.25. So my relative risk is 3. Now, to get the 3 times as likely, what you're basically doing is this. Pi 1 is 0.75. And in order to get up to that 0.75, when I compare it to pi 2 of 0.25, I need 3 of these 0.25s. So 3 times as likely. It takes 3 of these pi 2s to get up to pi 1. Now the 2 times more likely, again, if I start with pi 1.75, what that more is basically saying is that, okay, you're already starting with a 0.25. How much more am I? Well, I need 2 of these 0.25s, when summed together, to get up to this 0.75. So that's why there's a difference between saying as versus more. Here's another example. Suppose pi 1 divided by pi 2, my relative risk, is 0.6 divided by 0.4, or 1.5. So what this means is that a success is 50% more likely for group 1 than for group 2. Well, why? Pi 2 is 0.4. What's 50% of 0.4? Well, it's 0.2. So if I take 0.4 plus, if I take 0.2 plus 0.4, that's how I get to this 0.6. That's why I said more. Instead, I could say a success is 1.5 times as likely for group 1 than for group 2. I also have some other examples here to help you with the interpretation as well. Read those on your own. Okay, so then we come down to some questions here. What does a relative risk of 1 mean? Well, again, pi 1 over pi 2 When that's equal to 1, that can only occur if the two probabilities are equal to one another. This is a very important thing for us to investigate. Are the two probability successes equal or not? You'll see examples coming up. What is the numerical range of the relative risk? Well, we know that pi 1 is between 1 and 0, as is pi 2. So that means in this, when I take pi 1 divided by pi 2, of course, this has to be greater than or equal to 0. So my bottom bound is 0. Well, what's my highest possible value? Is it 1? Well, no, because again, I could have maybe pi 1 being greater than pi 2. And in fact, what that upper bound ends up being, you can see, suppose let's say pi 1 was equal to 0.9, pi 2 is 0.1. We can see my relative risk is 9. Suppose instead pi 1 was 0.99 and pi 2 is 0.01. Now my relative risk is 99, and as you can see that as that numerator gets bigger and bigger, the denominator gets lower and lower. Basically, I'm going up to a very high number, you could say infinity. So the numerical range ends up being between 0 and infinity. How can I estimate the relative risk? Well, all I need to do is put hats on top of the parameters that we don't know. By putting those hats there, I'm putting in the maximum likelihood estimators. And in the end, the maximum likelihood estimator for RR, called RR hat, is pi 1 hat divided by pi 2 hat. For those of you who've had a mathematical statistics course, you've heard of the invariance property of maximum likelihood estimators. That's why, by doing this little, putting the hats on it, that's why this is also the maximum likelihood estimate for RR. Well, what about doing inferences for RR? Well, I could do a walled confidence interval if I wanted to. We've talked about that many times before. You take the estimator plus or minus the 1 minus alpha divided by 2 quantile from a standard normal, take it times the square root of the estimated variance of RR hat. We will actually not use that. We'll have similar problems as what we've seen before. Now, instead, what we will do is still do a walled confidence interval. But we're going to actually find a walled confidence interval first for the natural log of RR. Depending upon other statistics courses that you've had, you may have seen instances where if you do a small, let's say, mathematical transformation of a statistic of interest, this transformed statistic tends to have a better qualities about it that make a probability distribution approximation work better. This is an example of that here. Excuse me. So working with the log transformation ends up getting you a better standard normal approximation than if you wouldn't have been working with it to begin with. So first we're going to find a confidence interval for the log of the relative risk. And simply, it's the log of the estimated relative risk plus or minus the quantile from the standard normal distribution times the square root of the estimated variance of the log of the estimated relative risk. What is this estimated variance? Well, it ends up being this. So 1 over the number of successes for group 1 minus 1 over the number of trials for group 1. And then we do a similar thing for group 2. Now, where does this come about? It actually comes about through using a delta method approximation. Don't worry about that. I'm not going to ask you for a derivation. If you're interested, take a look at Appendix B of my book. For those individuals who are taking this as a course and you are master's or PhD student in statistics, where you will see the delta method is in a second semester of a mathematical statistics course sequence. Sometimes you'll see it there. If you don't see it there, you will definitely see it at the PhD level when you take a course on large sample theory or asymptotics. Okay, so now I have this confidence interval for the log of RR. I want a confidence interval though for RR itself. So what do? I do essentially the inverse transformation of the log transformation, and that is of course then the exponential function. So I use the exponential function with what I just found from my previous interval, and there you go. There's my confidence interval for the relative risk. Now if we take a look back at this variance here, you'll notice that I have W1 in a denominator. I have a W2 in a denominator as well. What happens if you observe 0 successes for one of these groups? Well, you're not going to be able to calculate this value. So what's typically done in practice is an ad hoc solution is usually done, where if I have a 0 cell count in my 2x2 contingency table, what I can do is either add a small number to all the cells of that table and then do all the calculations as normal. So maybe I add a value of 0.5 to each of the 4 cells in my 2x2 contingency table. Or alternatively, what is sometimes done is that if, let's say, W1 was 0, just add a small constant just to that alone, like 0.5. Okay. So let's take a look at an example of how we can do these calculations. Excuse me. We're going to talk about the COVID-19 vaccine clinical trial involving the Pfizer vaccine. Here's the actual results that were released in, I believe it was November of 2020. So for example, 8 people who received the vaccine ended up being positive. 162 people who received the placebo ended up being positive in the study. So let me go ahead and come over here to 10 so I can do some of the calculations. So I'm going to put the data into a contingency table. I'm going to call it C.table for the lack of a better name. I could call it something else if I wanted to. Just to review, I use the array function where the data argument allows me to put in my data by column. It's a 2x2 table. My dimensions, or the names of the dimensions, in other words, the names of the rows, the names of the columns, are for my rows first. This is the treatment that people are being given, meaning they either received the vaccine or they received a placebo. It has, again, those 2 values. Then the outcome, after a period of time, these people, let's say, came back in to wherever the clinical trial was being done, and they reported if they were ever positive or negative for the disease, or maybe an actual test was being done there. So the outcome is that they at least one point was positive or negative for the disease. I put that again into C.table, and there's my contingency table. Similar to what we saw with a previous example, I can find my pi.hat table. So for example, the estimated probability of being positive for COVID-19 during this clinical trial period, given that you received the vaccine, is 0.00045. Here the same thing is for the placebo. So this is my pi hat 1, this is my pi hat 2. And so how about we just pull those out and create objects called pi.hat 1 and pi.hat 2. So just verify that. There we go. Now to find my relative risk, all I need to take is pi hat 1 divided by pi hat 2. And so that's what I'm going to do here. I'm going to round it to 4 decimal places and make it look a little bit nicer. So I get 0.0497. So what this says is that the estimated probability of coming down with COVID-19 is only 0.05 as likely if you receive the vaccine versus if you receive the placebo. So in other words, for this particular sample, you are much less likely to come down with COVID-19 if you got the vaccine than the placebo for this sample. What we like to be able to do now, given this sample of, I think it was about 33,000 people. How many was it again? Take a look. About 35,000 people. What we like to be able to do is take this sample of the 35,000 people and generalize it to the population of the entire world by using statistical inference methods. So to do that, we're going to find a confidence interval. So to find then, first of all, my estimated variance of the log of RR hat, what I can do is I find 1 over W1 minus 1 over N1 plus 1 over W2 minus 1 over N2. I put that into my object called var.log.rr. Then to find my confidence interval, what I can do is I take the log of the estimated relative risk plus my value, my quantile from the standard normal. And remember, since I'm doing this with two different values there for alpha divided by 2, 1 minus alpha divided by 2, I get the two values, the negative and the positive of 1.96. Take this times the square root of the variance, the estimated variance of log of RR hat. So let me go ahead and just run that segment of code for you. This gives me my confidence interval for log of RR. Because I want a confidence interval for RR itself, then I can use the exponential function with this entire part here. Put that into an object called rr.ci, for the lack of a better name, relative risk confidence interval. And then we can round both the lower bound and the upper bound to 4 decimal places by using the round function. So here's my confidence interval, 0.02 to 0.10. Let me come on back over here to my notes. So, standard interpretation then. With 95% confidence, the probability of infection, meaning probability of becoming positive, is between 0.02 and 0.1 times as likely for those individuals receiving the vaccine than for those individuals receiving the placebo. So we could see that it's unlikely for people to come down with COVID-19 if they have received the vaccine, or I should say it's much less unlikely, much less likely, I should say, to come down with the disease. And so then this then leads into a slightly different interpretation, especially in medical studies like this, where we're trying to prevent someone from coming down with a disease. We would like to know, well, how much has their risk of coming down with the disease or becoming infected, how much has the risk been reduced by taking the drug versus not taking the drug? And so because of that, then, very often you will see people, instead of using 0.0497 and interpreting that directly, they will interpret 1 minus 0.0497, which would be then 0.9503. So what this says is that if your probability of coming down with the disease was 0.05 as likely by taking the drug versus not having the drug, in other words, having the placebo, then conversely you could say my probability of becoming infected is reduced by 95% by getting the vaccine than the placebo, by using this 1 minus the relative risk. You could also then do the same exact thing with the confidence interval. So with 95% confidence, the vaccine reduces the risk of infection by 90% to 98%. This 1 minus the relative risk has actually a special meaning or a special name when dealing with vaccine clinical trials. It's referred to as the vaccine efficacy. So if I call that VE, VE is equal to 1 minus RR. During 2020 and also into 2021, many news media outlets were stating the vaccine efficacy for these various clinical trials that were concluding during those years as we were trying to look at ways to prevent infection from COVID-19. So for example, this is, I think again from November of 2020, in the New York Times, this was their headline when the Pfizer results were publicized or released, I should say. New Pfizer results, coronavirus vaccine is safe and 95% effective. This is 1 minus RR hat. Now, of course, I would like the New York Times to state that this is and is safe and estimated to be 95% effective. That would have been a more precise way to word this, but they just chose to say it this way. You will even find that some of these news media outlets were actually stating the corresponding confidence interval as well. Very often, though, they won't say it's like 95% confidence. They just say, well, the vaccine efficacy would be between 0.9 and 0.98, or 90% to 98%. Okay. So sometimes we are also interested in these situations when we're working with the relative risk, is that we would prefer to always interpret a relative risk that is always greater than 1. Sometimes it's a little bit easier to word the interpretation that way. So in our particular situation where we had a relative risk of 0.05, which would be pi 1 divided by pi 2 estimates, we might want to invert it so that 1 over RR hat is equal to 1 over 0.05 or 20. And so this is pi hat 2 divided by pi hat 1. And so what this is saying in our particular situation is that the estimated probability of infection is 20 times as large for the placebo group than the vaccine group. This kind of interpretation wasn't used at all with the COVID-19 vaccine clinical trials, but there are other situations out there where doing this inversion, always having a relative risk greater than 1, can make then the interpretation just a little bit easier. And one way to think about that is to go back to some of my original interpretations when we looked at the 0.6 divided by 0.4, where you had a relative risk of 1.5. Now notice when I do interpret this confidence interval then, if I come up to the original interpretation, notice I do not say with 95% confidence the estimated probability of infection is between 0.02 and 0.1. This is sometimes a common mistake that students make where they add the word estimated. The word estimated should not be there because we are actually finding a confidence interval for the actual parameter itself, RR, rather than its estimated quantity. So in the end, would you rather be in the placebo or the vaccine group here for this particular situation? Or maybe actually I should probably change that. Would you rather, let's say, receive the vaccine or actually receive the placebo? Well, obviously there's various thoughts on issues with vaccines and stuff, but if you were just to rely on the statistical results alone here, you would say, oh, I prefer to receive the vaccine because I know my probability of infection is much, much smaller than if I wouldn't receive the vaccine. Okay, here's another example. Now this goes to the Larry Bird example that we've been discussing a number of times. In this particular example, one probably wouldn't want to use a relative risk with it because the estimated probabilities here are so large. Again, relative risks are best used when your probability of successes are small. But if one still wanted to calculate the relative risk, here's how you could do it. And I will let you, on your own, to go through this example to see how the calculations would be made. Basically what I've done here, and corresponding to what I've said before, is I took my COVID-19 example, the programming code, I took it as a template, and I created a new program corresponding to Larry Bird here that will do these calculations now just for a different contingency table. Okay. Lastly, similar to what we've seen before for confidence intervals for pi, confidence intervals for pi 1 minus pi 2, there have been a number of other confidence intervals proposed for the relative risk. The one that I gave you is most commonly used, and it's a very good confidence interval. It performs well corresponding in comparison to other confidence intervals. That's why I chose to do that one. There is another confidence interval that can perform quite well as well, and this is based upon a score confidence interval. If you're interested in actually using that or learning more about it, take a look at the function called risk score CI that's in the prop CIs package. Okay, so that concludes then this section on the relative risk.